I will read some sentences from that I try to summarize from the CV of Professor Sharma, but I have to tell you that it was difficult because the CV is so full of words and important things that it was difficult to find out a summary. Anyway, it may be that you have to say something to what I'm saying, that the Professor Sharma is the Director of Research of the International Experimental Central Nervous System Injury and Repair, University Hospital of Uppsala University in Sweden. He is Professor of Neurobiology, teacher of Neuroanatomy, and is affiliated with the Department of Surgical Sciences, Anesthesiology, Intensive Care in Uppsala University. After her bachelor and master degree in India, he got the PhD in neuroscience in Varanasi, and it was awarded. This was one of the first awards, because there are so many awards he received in his career, for the best PhD thesis on the blood-brain barrier stress. Then, after some series of government funds in India, he moved to Uppsala University and began to investigate the transfer across the blood-brain barrier caused by stress or traumatic insults to the brain and spinal cord. Then he established a network collaboration as a lead investigation with all the parts of the world. And he also received a prestigious anatomy award for his University on Hyperthermia in Uppsala University, where he received also the degree of Doctor of Medical Sciences. Then his research, his interest is as well is in neuroprotection, neuroregeneration, in relation to the blood barrier stress, trauma, drugs or abuse in health and disease, and especially in hypertension and diabetes. Recently, he's also moved to the new area that you of course know, that is nanomedicine, to find out the role of nanoparticles in neurodegeneration and neuroprotection, using different treatment strategies. I skip this because it's a list of the awards that he received.
Okay.
He's also president of the Global College of Neuroprotection and Neurogeneration, president of the International Association of Neurorestoratology, okay, and is member of, no, excuse me, he is editor of different journals, and he published more than 400 papers, 85 reviews, 40 monographs, 80 international book chapters, and edited 18 book volumes. He is editor-in-chief of Journal of Neuroprotection and Neurogeneration, and reviewer of all the journals of the world, and is working over 30 years in the blood-brain barrier, and that's the reason why we invited him to give this lecture today. Please.
Thank you. This is an honor for me to be here in Milan. First time to any university in Milan, and I will share. I know Professor Masrini from his work on nanomedicine. We are deeply impressed, and one of the reasons I'm here that together with my wife Aruna and one of my colleagues from Romania, Professor Milan, we are editing a volume of Springer materials and gene delivery to the central nervous system, nanotechnological advances. This will be published as an e-book by Springer New York, and I would like very much to both students or researchers who contribute to this chapter. The book is scheduled to be published later this year in 2016. So that is my contact. We are establishing nanomedicine or nanotechnological advances at the level of CNS, and we are very frequent. The idea of this book was generated in one of the National Innovation Summit and showcased in United States government that is organizing every year in May in Washington DC. So So we have conceptualized this idea, and now I want a contribution from Professor Masrini and his group. I will briefly today share some of our works on nanomedicine that we have understood, and I will show you some of our experimental observations obtained in a network of collaboration. Before I move, I can tell you that this is a collaboration by various organizations and Wright Patterson Air Force Base at US military is supporting the basic idea that we started in 2004 with this collaboration, and also this United States government, Swedish Strategic Research Foundation, European Office of Aerospace Research and Development, National Center of Toxicological Research, and I have also one partner from the University of Modena from Italy. He is very active, Giovanni Tosi, and he is working on the development of nanoformulations across the blood-brain barrier. This is the Office of Air Force Research. We have some companies, Pharma in Austria, AstraZeneca in Sweden, and we are also working now as a partnership with the University of Basque Country in Bilbao. This is my hospital. That is, in terms of Italy, it is very young. It is just 300 years old. And here is my Uppsala University. That is also 1476, but I think the oldest university lies in Italy. So we are very honored. And this is the latest institute developed in partnership with government and private partner players, Raw Neuro Institute of Neurology and Diagnostic Center in Cluj-Napoca in Romania. That is my collaborator, Dr. Morisani, is there. So this is a worldwide collaboration in EU and US countries. And of course, I would like to say that whatever I am telling, this is my personal view. It has nothing to do with any government organizations or funding agencies that I am working. So all is my personal views. Part of this is working on nanotechnology as a tool for crossing the blood-brain barrier, and there are various ways. In a nutshell, what we would like to study that whether nanoparticles itself can open the barrier, and if it is true there is pathology coming or not, because this is very important, because we want to develop the drug or transfer to the brain, and we want to breach the barrier. The problem is nanotoxicology, and this is the work we are doing together with US FDA and also the Air Force Research, and then try to develop some formulations. As mentioned, I did my PhD in 1982 on blood-brain barrier in stress, and that's why my thinking was that why all people cannot get neurological diseases, why in some people Alzheimer or some psychiatric diseases. Probably this is the effect of environment or many other things that opens the barrier and leading to brain pathology. Nowadays, this is quite clear that when we study brain, we think about neurons. But now, since last 10 years, it has emerged that not only neurons, the glial cells are participating equally for the development of brain function and also controlling the disease. But what is not very well looked is the endothelial cells, that the physical barrier for the brain. There is a barrier between blood and brain. So we focus our research largely on the endothelial cells, because when it is open, it can influence both glial cells and neurons as well. So we summarize some of our hypotheses in this book in 2004, and because we consider that blood-brain barrier is the gateway for all neurological diseases. If this is the gateway of neurological diseases, surely it should also be the gateway for therapeutic purposes. The point is that in all neurological diseases, we have leaky barrier. Good point is that we have several drugs that can influence the blood-brain barrier to restore or even to open. One of the first anatomical result was carried out by Brightman and Rees at the NIH, and they showed that this lanthanum, that is only 12 angstrom in diameter, is stopped by tight junctions between the two endothelial cells. And this was the first anatomical demonstration of the physical side of the blood-brain barrier. While working in Free University Berlin clinical anesthesiologist at that time, my professor George Navarro, he was the director of Neuropathological Institute in Berlin at that time. We were working on hyperthermia. Hyperthermia is quite a problem, and in many places people are dying. And hyperthermia is also a problem for cancer treatment because this is given as whole body hyperthermia. At that time, nothing was known what is happening to the brain. So after working a lot, we are working on this hypothesis. Any CNS insert will open the blood-CNS barrier. What I mean the CNS, because we also have blood-spinal cord barrier. And the spinal cord, there are minute differences between blood-brain barrier and blood-spinal cord barrier. So I club this term blood-CNS barrier. When it is open or broken down, edema will follow, necrosis, ischemia, and also cellular changes. All together can lead to cell death. So our point is that whether we can block this at this level or this level to induce neuroprotection. Now, considering our association with different government and military organizations, we find that our soldiers are facing difficult time. And for example, they are exposed to some Middle East where the sands are quite often, and they have silica nanoparticle exposure almost every day. And the point is that when there is any injury to the brain in normal situations in healthy environment, and when the same kind of insult is given to our soldiers, they are having exposed to sand particles every day, will it be same? I believe not. The pathophysiological changes would be quite different. We are also working on the hypothesis that whatever the animal research is doing in all over the world in the laboratories on healthy animals. But on the other hand, when we try to develop the drugs for treating human beings, you know that after 40-50 years, very seldom healthy human being can be found. They have endocrine problems, they have cardiovascular problems, and even they have traumatic injury or whatsoever it is. So if we try to deliver the same kind of medicine to these people having these complications, I think that's why we have failed from bench to the bedside. No drug is developed based on any experiment that is successful in human cases, because this is very difficult in human patients. So therefore, we believe that when the injury occurs in these soldiers, situation will be entirely different. Look at this situation. Nowadays, it is quite common in many parts of the world. This is missile explosion, this is carbon, sulfur, many other nanoparticles are exposed, and these persons are exposed every day. So we have to think that their pathophysiological conditions itself, without any injury, is changed or not. Their brain function could be altered. This is the other file picture from US government when the soldiers are landing. You know, there is dust storm, and they are all exposed to this situation. That is one of the pictures. You can see that it's a lot of problem. When they get injured, a lot of problem could occur that is not treatable in healthy environment. This is another example. You can see what happens to the people living around the area. So, in 2009, we tried to highlight this problem, and we edited this book, Nanoneuroscience and Nanoneuropharmacology, in Progress in Brain Research series. And what we have focused, that we need to understand this nanomedicine aspect in both ways. The toxicological aspect of nanoparticles and nano delivery of the medicine. And then still we have the problem that if we use these nanoparticles, and some of them are biodegradable, but some of them are not. So they can stay in the central nervous system for a long time. What is the long-term consequences? So these are the problems. Still we do not have answers, but we are working on those. This is one of the Nobel laureates, Dr. Aaron Chikanover, and after his suggestions, he got the Nobel Prize on ubiquitin expression in the CNS. Some of you know very well. And then we are trying to understand what will happen when the nanoparticles can change the ubiquitin expression. On the other way, can we use drugs to modify ubiquitin for neuroprotection? The question we are asking every day in our group, that why we use nanomedicine, for what purpose? There are some aspects that it can enhance the drug effect, same drug than the normal. If we give drug X with nano delivery, maybe it has much more better efficacy in the central nervous system. Could be long-lasting effects, rapid penetration into the CNS, and obviously less degradability. It is less degraded when it is combined with drug and nano formulation. All these are speculations, we are working on this. But what about the neurotoxic effects? Widespread distribution in CNS could occur, but what is happening about neurotoxic effects? Then the question we ask, there are different modes of delivery of nanoparticles. And the point is that if we use 10 different types of drugs using same type of nano delivery, all drug could be better by simple nano delivery, or the drug specific effects could be enhanced only. What is the chance of neurotoxicity versus neuroprotection? And of course, the neuropathological aspect of nanomedicine is still widely ignored. The reason is that most of the nanomedicine or nanoparticle studies are done in vitro, and only 20 to 30% experiments are done in vivo. I am basically trained as a neuropathologist with Professor Ingve Olsson in Uppsala University. So I believe that even the neuroprotection or neurotoxicology I should examine under light microscope or electron microscope. That is my specialty. Then we summarize some of our works in new concepts of neuroprotection long ago. I think this is 2012. We work with US FDA, is the director of National Center of Toxicological Research, US FDA Arkansas, Dr. William Seeker. He is our co-partner in many research projects. Then I show you some brief example of nanoparticle exposure to the central nervous system. My wife was invited for this San Antonio brain injury, North American Brain Injury Association analysis in San Antonio recently. The idea is that sleep deprivation is one of the important aspects in military. And when they work in combat or even peaceful expedition, they have to awake and sleep is really disturbed. This is an example how our soldiers are sleeping sometimes or just have a short nap. They have fatigue, and this will influence their performance, both cognitive and sensory. This is an example from military data that they were average scores, for example, in 2000, 2001, and 2003. When they were deprived of sleep, their average scores were very less. When they have allowed for 8 hours sleep per night, their average score was much better. So sleep deprivation is one of the important aspects when our ability for cognition and function is severely deteriorated. Obviously, the sleep disturbance is chemicals that are released in the brain can influence our function. So this is an example also from the data. 72 hours sleep deprivation on performance and serial, they cannot do even simple addition or subtraction. This is an example, 24 hours, 48 or 72 hours. So you see that when these soldiers were deprived of sleep, how they can function to their optimal level. This is another example, different type of functions. You can see that 4 hours sleep is the worst, 5 hours, and 7 hours sleep is still good. So our first question was asked, do we have temporary or permanent changes in the brain when the animals were exposed to sleep deprivation? Obviously, we cannot mimic human cases in the laboratory, but there are standard models to induce sleep deprivation. So this is in the rat, and there is an absolute good method published in Neuropsychopharmacology long ago, inverted flower pot, when you put in water pool and rats were placed there, and when they have sleep, they can fall down in the water, so their sleep is disturbed. So in this model, you can see that what we have done is 12-hour sleep deprivation, 24-hour, 48 and 72 hours. Normal rats were given only sleep deprivation. You can see in the cortical areas there are so many neural cells were distorted or damaged. Our animal ethic permission does not allow these animals to survive for a long time. So at the moment we do not know whether these changes are permanent or temporary. Okay. Then we added some nanoparticles, copper nanoparticles, silver nanoparticles of two different sizes, 20 to 30 nanometer and 50 to 60 nanometer. But we can see that the smallest nanoparticles, they have possibility to damage much more than a bit larger nanoparticles. Also we see that silver nanoparticles have much more adverse effect on the same concentration than the copper. So this gives us an idea that size of nanoparticles is important, but also the constituent of the nanoparticles are equally important. Here you can see when we have, then we tried to give some drugs. And sleep deprivation is the problem of serotonin altered metabolism. Serotonin has more than 7 receptors and various subtypes. It is very difficult to choose, but this was pilot experiments. We use ondansetron. This is 5-HT3 receptor antagonist. There were two examples. One, we have given ondansetron alone, and then we have given ondansetron level on nanowire formulation. What you can see, these are silver, copper, same size, 48 hours of sleep deprivation. You can see that ondansetron alone was able to induce in 2 milligram dose some neuroprotection. But when we have given with titanium nanowire tag the drug, we have better neuroprotection here as compared to the compound alone. So the message is that when we deliver the same compound using nanowire formulation, this is a patented nanowire technology in the University of Arkansas with my friend. So it can not only have better effect, but also it has reduced the dose and have better neuroprotection. So this is just an example that we were given certificate of excellence in US FDA long ago for that. These are nowadays, these are the different way of nanowires, and I'm showing the others work in support of our works. The dexamethasone was given in this technology on spinal cord injury, and they got very nice protection. This is the paper, you can follow later. So corroborating our findings. Then there is also, we have written a review, invited review in amino acids, and what we can say that when we modulate the basic healthy situations with either diabetes or hypertension, we have much worse effect. And when we give the drug to treat the normal healthy conditions, they are failed when the animals were combined with diabetes and hypertension. But when we provide nanowire delivery of the same drug, we have some better effects. I will show you some examples of this. Nowadays, one of the important problems we are facing is Alzheimer's disease, and many drug companies are interested to find a cure. Of course, cure is very difficult to attain in any cases. But what we can do or try to do to reduce the progression of pathology so that still we can have some quality of life for some time as compared to not given any drug, right? So, to this audience, I don't need to explain that why, but to some of the students, I can explain that Alzheimer's, this is the lady, was first described by a German scientist in 1902, and that's why with his name, the disease was named Alzheimer's disease. As a pathologist, you can see that this is the normal human brain and this is the Alzheimer brain. You can see that brain has shrunk almost completely. So we have, it is obvious that almost all higher functions are compromised. As I told you that in brain we have these blood vessels, astrocytes, neurons. So in Alzheimer disease there is a deposition of amyloid peptide here, and then it can disrupt the connections between neurons, glial cells and microglia, so making all problematical. We came across to a compound called cerebrolizin in 2005. It is commercially available by an Austrian company called Neuropharma. It has some clinical trial going on in the United States, so it is well-established drugs, and it has a clinical trial going on in different parts of the world with stroke, brain injury, and Alzheimer's disease. So, being a basic pharmacologist, we wanted to study its effect on some of our animal models. This is a multimodal drug, means this is a mixture of different types of neurotrophic factors, active peptide fragments, and it has various possibilities. So what we did, we tried to nanoformulate this compound and use in same our model to find out whether the nanodelivery of this compound is better than the normal. I can tell you that the nanowires were developed by Dr. Young in University of Berkeley for electronic purposes. He was the father. Then in Arkansas, my friend Dr. Brian Tian modified this nanowiring from titanium and have a US patent on titanium nanowire papers. This is now ex-governor, but he is supporting our research on nanowiring. And this is Dr. Ryan Tian and this is Dr. Wang. They have the US patent of these titanium nanowires. So we label the drugs in their laboratory according to their methods so that we do not make any mistake or the standardization will be efficient. This is the picture of one of the titanium nanowires used. Nowadays, nanowires are used for also various purposes. I'm quoting some examples. When stem cells are grown on nanowires, then they live longer and they are not dead, and their manipulation or growth is very fast. We have submitted a work for innovation on nanowire delivery of cerebrolizin in animal model of neuropathic pain. To our surprise, in 2013, this National Innovation Summit in United States, Washington, D.C., they found that this technology is top 20% of the drug development, and we got the award by US government. This is very prestigious for us and we are very honored. But not only honored, we understand that this was a rigorous evaluation, so our methods and our system is working in right direction. Even this came to spotlight on cerebrolizin treatment of neuropathic pain using nanowire. So we are happy that we are going. Now I am showing you some experimental observations in rat model in our laboratory. So this is the mouse model of Alzheimer's disease, and you can see that it is still controversial that deposition of beta is the cause of Alzheimer's disease or it is just an effect, but this is very clear that all Alzheimer's cases, this beta amyloid peptide is present in the brain. I am not going to controversial theories, but we have measured this A beta in cortex in control situations, and this is the mice where we have this great deposition of amyloid beta. We make this model by infusion of beta amyloid peptide with a standard method. You can develop this. When we have given cerebrolizin alone, you can see that there is reduction. But nanowire cerebrolizin resulted in almost near control level in situations of 3 weeks. We have not followed beyond because of our animal permission, but until 3 weeks, we can find this situation that is very much encouraging.